All right, so in the last part of this lecture, we went over random variables and some of the general concepts surrounding them, like probability distributions. Then, we introduced a few probability distributions that are common in ecology: the Bernoulli, binomial, Poisson, and normal distributions. Now, we want to use what we've learned to find good estimates for our parameters in our model. To do so, we have to define the likelihood function. Recall from basic probability theory that the probability of two independent outcomes, A and B, is just the probability of A times the probability of B. If two flips of a coin are independent, for example, then the probability that two of the flips will be heads is just 0.5 times 0.5, which is 0.25. When we calculate a likelihood, this is all we're doing. Once we've chosen a probability distribution and its parameters, we calculate the likelihood of those parameter values by evaluating the probability density or probability mass function on each of our data points and multiplying those values together. So the likelihood for a given set of data points, x, and a given parameter value, theta, is the product of the probability mass or probability density of each of our data points given theta. Here's an example that might help illustrate this. Let's say that we have 5 data points and they're all either 0 or 1. Because they're all either 0 or 1, it seems clear that these are the outcomes of a Bernoulli distribution. We're going to assume these data points are independent of each other. Now, to calculate the likelihood at a particular value of the parameter p, we're going to take each data point and we're going to plug it in and that parameter value in to the Bernoulli probability mass function and multiply the outputs together. So let's say that p equals 0.5. So the probability of the outcome being 1 is 0.5. And the probability of the outcome is 0 is 0.5. If these are our 5 data points, then the likelihood for p equals 0.5 is 0.5 times 0.5 times 0.5 times 0.5 times 0.5. It's 0.5 to the 5th because we have 5 data points, which is 0.03125. Now, let's instead assume that p equals 0.6. So the probability of the outcome is 1 is 0.6, and the probability of the outcome is 0 is 0.4. Now the likelihood for p is for p equals 0.6 is 0.4 squared times 0.6 cubed. That's 0.03456. It doesn't seem like a huge difference between this and the value we got for p equals 0.5, which was 0.03125, but notice that the likelihood is higher when p equals 0.6 than when p equals 0.5. Now let's do this for every possible value of the likelihood between 0 and 1, or every possible value of the parameter p between 0 and 1. But let's also add the data points one at a time because it'll help illustrate a couple of things about the likelihood function. So starting with the first data point, let's plot the value of p on the x-axis and the likelihood on the y-axis. Since our only data point is 0 here, the most likely value of p is also 0. In other words, if we knew absolutely nothing about coins and we flipped a coin once and got tails, we'd be inclined to say that the only possible outcome of the coin is tails. Also, we know that it's not possible for the only outcome to be heads. In other words, for p equals 1, because the coin gave us tails. So likelihood is 0 at p equals 1. Next, let's do this for 2 of the data points. There's 3 things I want you to notice here. The first is that since our data now includes both a heads and a tails, the likelihood is 0 at p equals 0 and at p equals 1. In other words, we know that this coin isn't only heads and that it isn't only tails. The second thing to notice is where the peak is. It's at the average. With just these 2 data points, we now think the most likely value of the parameter p is 0.5. Now, it won't always be this easy to find the maximum likelihood estimate, which is 0.5 here. If it was, then why not just take the average, right? But it's nice to see that for a simple problem, the peak of the likelihood function occurs at an intuitive place. The third thing to notice is that the scale of the y-axis is smaller. Because we're multiplying probabilities together, and the probabilities are always between 0 and 1, the likelihood function gets smaller as we add more data. Now let's see what it looks like with all of the data. As you can see, the y-axis scale does get smaller as we add more data. And the peak of the likelihood function is always at the average of our data points, which is 0.6 for all 5 data points. The last thing I want to add is that, the last thing I want you to notice though, is that the curvature around the peak gets steeper and steeper with more data. With n equals 2, the peak is quite broad. But with n equals 5, the peak is fairly narrow. We'll come back to this when we talk about confidence intervals, but basically this reflects the fact that as we get more data, we become more certain in our estimates. I just want to add that although I showed the likelihood function for various amounts of data, the only likelihood function that matters for maximum likelihood estimation is the one with all of our data. These other plots were just to illustrate how some of the properties of the likelihood function relate to our sample size. It's actually quite easy to code up a likelihood function in R. For a normal distribution, we can write this function that I'll call LNorm, which, given a mean mu, a standard deviation sigma, and some data points x, returns the product of the normal density, or the density under the normal distribution, of the x values given the mean and standard deviation. If we want to do this for a binomial distribution with parameters p and n and our data points x, the code is very similar. Now, what if we have x and y values and we want to express the likelihood of the y values assuming that y is a linear function of x? In other words, what if we want to write down the likelihood function of a linear regression? Well, it's not that much more complicated. We now have three parameters: the intercept alpha, which is actually a here, the slope beta, the standard deviation sigma of the residuals, and we have two vectors, x and y. The likelihood statement for y here is almost exactly the same as the likelihood statement in the first example, with the product of the density under the normal distribution of y given mu and sigma. But now mu equals alpha plus beta times x. One last example of this, the likelihood for logistic regression. We need to do one more thing here, define logistic transformation. But once we've done that, the code is again very similar. Pause the video and take a minute to parse through the code inside the logistic like function. See how we're still just using a binomial likelihood statement, but now the parameter p is a function of x. And just as a reminder, if some of this stuff is going over your head, no worries. We're going to spend the rest of the week applying and reinforcing this. All right, so by now you might have guessed where the maximum likelihood estimate is. It's just the value of a parameter for which the likelihood function reaches its peak. In the example we went through, the maximum likelihood estimate was p equals 0.6. This also extends to multiple parameters. Let's say, for example, that we have two parameters we want to find the maximum likelihood estimates for. These could be, for example, the mean and standard deviation of a normal distribution. In that case, we have a likelihood surface, and the joint maximum likelihood estimate for these two parameters occurs at the peak of this surface. We can extend this to as many dimensions as we want, though of course once we have more than two parameters, this becomes a hypersurface, and our weak mortal minds have a hard time picturing that. Now, in the simple example we went through, it was pretty easy to pick out where the maximum likelihood estimate for p was. But for real problems, how do we actually find the maximum likelihood estimate? The first way is by taking the derivative of the likelihood function with respect to our parameters and solving for the maximum likelihood estimate, which occurs where the derivative is 0. We can do this manually. I'm not going to cover this because it's just not feasible for complex models. Another way is grid search. This is where we just evaluate the likelihood function for a lot of different values of our parameter or parameters and return the value with the highest likelihood. We're also not going to do this because while it's intuitive, it becomes really computationally intense for more than a couple parameters and it's imprecise. What we'll do instead is use numerical optimization methods that are already implemented in R, which we can access using the optim function. There are several different methods available, but I'm not going to go over how they work because it's not really necessary for this class. If you want a good overview of the frequently used methods and how they work, check out Chapter 7 of Ben Bulker's book, Ecological Models and Data in R. In order to use numerical optimization methods, however, we're going to have to make a small modification to our likelihood function. Remember how, as we kept adding data points, the value of our likelihood at the maximum likelihood estimate kept getting closer and closer to 0? Well, this is a problem for computers, which will have a hard time finding a peak when everything around the peak is also really close to 0. So instead of maximizing the likelihood function, we're going to minimize the negative log likelihood function. These produce the same result, but are computationally easier because the negative log likelihood is not going to approach 0 as we add more data, and because on the log scale, we're dealing with sums instead of products. Let's go through a couple simple examples of what finding the maximum likelihood estimate in R looks like. This function, which we'll call normal log like, returns the negative log likelihood of the mean mu and the standard deviation sigma given some data x. It's pretty similar to the one we already wrote out to calculate the likelihood, except we've added an argument, log equals true, to the dnorm function. and we're returning the negative sum instead of the product. We're going to have to make this just a little more complicated, however, if we want to pass it to a numerical optimizer. We're going to change this up in two ways. The first is that we'll have to pass all of the parameters we want to optimize as a single argument, which here I'll call par. So now there's only two arguments, par and x. Inside the function, we separate par into the two parameters we want to optimize, mu and sigma. The next thing we have to do is check that the parameters make sense. In the case of the normal distribution, we know that the standard deviation cannot be negative. So we'll only return a log likelihood, a negative log likelihood, if sigma is greater than 0. Otherwise, we'll return some arbitrarily high number. In this case, I used 5,000. There are packages that we can install if we'd like to do constrained optimization. That is, if we'd like to just tell the optimizer not to even try parameter values that don't make sense. But we really don't have that luxury with base R, so we're just going to return a really big number for parameter values that don't make sense. Now let's simulate 1,000 data points for a normal distribution with mean mu equals 4 and standard deviation sigma equals 2, and use our function to estimate mu and sigma. To do this, which, I mean, of course we know sigma and mu, but we want to make sure that the maximum likelihood estimates that we get are similar to the known values. To do this, we use the optim function, and we give optim some initial values to start with. For something as simple as this, it doesn't really matter what initial values we pick, but it will definitely matter as the problems get more complex. Then we give it our negative log likelihood function, and any other arguments our negative log likelihood function needs to run. In this case, that's x. When I ran this, here's what my data looked like. And here's what the output of optim looked like. It contains the maximum likelihood estimates for mu and sigma, which, as we expect, are close to the true mean and standard deviation. It includes the value of the negative log likelihood at the maximum likelihood estimate, and then some metrics on how many iterations it had to do to get to the maximum likelihood estimate. Then it contains a code for whether or not the model converged, which is 0 if optim thinks the model did converge. But I find that for complex models, this code is basically useless, to be honest. It might also contain a message if something went wrong. Let's do this for a slightly more complex model, a linear regression. You can see that all we've done to change our negative log likelihood function is add an argument y, broken our par argument out into alpha, beta, and sigma instead of mu and sigma, and then assign mu as alpha plus beta times x. We then simulate some data where the intercept, slope, and standard deviation around the regression line are all 2. Our x values are 50 random values between 0 and 10, and our y values are random values from a normal distribution with mean alpha plus beta times x and standard deviation sigma. The optim call here isn't very different either. We specified a different function to optimize, given initial values for the intercept and slope as well as the standard deviation, and added y as an argument. When I ran this is what my data looked like. And this is what the output of the call to optim looked like. As you can see, since we only have 50 data points this time, the maximum likelihood estimates aren't quite as close to the values we use to generate the data. Pause this video and make sure the code makes sense to you, especially the negative log likelihood function. If you're confused though, no worries. We'll be using the same negative log likelihood function for our lab on Monday, so you'll have more opportunities to make sense of it. Before wrapping up this part of the lecture, I want to talk about one more thing, which is how do we visualize how the likelihood depends on our parameters? So far, we've introduced 2 ways. When we have only one parameter, we can just plot the value of the likelihood across different values of our parameter as a curve. We call this intuitively a likelihood curve. When we have 2 parameters, we can plot a likelihood surface. But what if we have more than 2 parameters? In that case, we can't visualize the dependency of the likelihood on all the parameters at once with a single plot. So we have 2 options. The first option is just to pick 1 or 2 parameters that we're interested in and hold the other parameters constant, preferably at their maximum likelihood values, so that we can plot the likelihood as a function of just the parameters of interest. This is called a likelihood slice because it's a slice through the likelihood algebra surface. The second option is for us to pick a parameter that we're interested in, and for a bunch of possible values of that parameter, we find the maximum likelihood estimates for the other parameters while holding the parameter of interest constant. In this way, we're visualizing the maximum obtainable likelihood for a given value of the parameter. This is called a likelihood profile, and it's a really nice way to visualize the dependency of the likelihood on our parameters of interest without the other parameters messing it up. One thing that I do want to add is that these definitions are not universal. I've seen like 4 different definitions for the term likelihood profile. However, these are the definitions we'll be using in this course. So how do we go about computing a likelihood profile? Well, if I asked you to do this from scratch in a language of your choice, it would look like this. First, for a parameter of interest, theta 1, we'll pick some value. Then we obtain maximum likelihood estimates for the other n-1 parameters, which we'll call theta 2 through n, while holding theta 1 constant. Once we've obtained those estimates, we record the likelihood or the negative log likelihood at those estimates. We repeat this for a range of possible values of theta 1, typically centered on its maximum likelihood estimate. Here's the R code for such a procedure, where we've got a normal distribution with parameters mu and sigma, and we want to plot a likelihood profile for mu. So let's define this function, which we'll call mu underscore prof-like, which is exactly the same as the negative log likelihood function we already wrote for the normal distribution, but now we've pulled mu out of the parameters argument. So we're passing mu to the negative log likelihood function as its own argument, and otherwise the parameters, which are in this case are just sigma, stay in the par argument. This means that only sigma is going to get optimized by the optim function. Mu is going to be held constant at whatever value we pass to this function. I'll simulate some data here, but of course you'd normally be applying this to a situation where you already have data. What we'll do is create a sequence of values from mu that we want to plot the likelihood profile for. And then we'll initialize an empty vector to store the negative log likelihood, which I'll call mu underscore NLL, at each of these values of mu. Finally, we loop over the values of mu, and we optimize the value of sigma with our mu underscore prof-like function, passing mu not as part of the parameters to be optimized, but as an additional argument. Then we store the negative log likelihood at that optimized value of sigma. Here's the negative log likelihood profile plot that I got when I did this. We can see that the negative log likelihood increases as you go further from the maximum likelihood estimate of mu. Anyway, that's it for the second part of the lecture. In the last part, we'll be going through different ways to estimate the uncertainty in our parameters.